Record to the Scranton crowd. Here we go. Just some quick housekeeping, just a reminder to everyone, if you would mute your microphones during David's talk so we can have a nice clear conversation, and obviously unmute when we're ready for questions and stuff later on. Thanks. As we come up to 4 o'clock, I want to thank Mary Lou again for using her Cornell connections for arranging today's speaker. So this is 2 in a row. This is fantastic. We've got a friend of Gwen's coming up in January. It'll be January 8th, maybe a little earlier in the year, but we want to keep things on our regular schedule. We're going to learn some more things about whisper and whisper capabilities. So more information to come on that early in January. So it's 4 o'clock. So I will say welcome everyone to the Thursday, December 11th version of the HamSCIence Zoom presentations. Today, we are very fortunate to have Dr. David Hysell, KY2W, from the Department of Earth and Atmospheric Sciences at Cornell University. And Mary Lou, you got a little bit of an introduction, so let me turn it over to you.
Okay, well, welcome everybody. David Hysell earned his PhD from Cornell in 1992, and I know him because of the Cornell connection. I was an undergraduate at Cornell. He investigates ionospheric plasma physics with a focus on plasma instabilities and their effects on radio wave propagation. Communication outages caused by ionospheric irregularities are a central component of the National Space Weather Program. These instabilities are found in the equatorial and auroral electrojets, and in the middle E-region ionosphere, and in equatorial and mid-latitude spread F. The research is both experimental and theoretical and has a substantial computational component. An important research tool for studying the equatorial ionosphere is the Jicamarca Radio Observatory near Lima in Peru. It's the world's largest radar. In the spring of 2005, Dave Hysell became the PI for the NSF cooperative agreement that supports this radar. So we would like to welcome and hear all about it.
Well, great. Well, thanks very much, Mary Lou, and I always appreciate the Cornell connection. And thanks, Gary. And if you don't mind, I'm gonna turn off my camera because I have a face for radio anyway, and I'm gonna share my presentation with you here. And so I hope you can see that. And so let me just start out by saying I'm a ham. I was a ham when I was a little kid, and I was always interested in transceivers and antennas, and also in radio wave propagation. And I got to do the greatest thing, which is to parlay this into a career. So I'm probably not as good a ham as I should be because my day job is radio, and I get to use all kinds of fancy pieces of kit. So I'm showing you a picture of this radar that Mary Lou was talking about. It's in Peru, and it's enormous, and it works at 50 megahertz, and it's made up of approximately 10,000 cross dipoles, fed by 4 megawatt class transmitters.
We're not seeing it.
Oh,
please.
I'm seeing your title slide.
Yeah. Okay, so that's it. So big. So we'll probably have a little bit of a lag. So big array radar here. And we used to study the ionosphere, and we've been doing that for quite a few years. And it actually measures all the state parameters in the ionosphere, electron number densities and temperatures and composition and drifts, and one can extract information about winds and all kinds of good things. And so we use this to study what's going on ahead of above us. And so that's been sort of a great facet of my career. But I want to add that I also get to work with medium-sized apparatus and smaller apparatus, and there really being a ham has been more useful to me than what I learned in school. let's see, did my slide update?
Booker and Wells, 1938.
There you go. So a little history here. So this is older than any of us, and it's a article from the 30s, and it's an ionosphere observation, ionosphere measurement. And this ionosphere, it's a pulsed HF radar, and it was deployed in Peru really before there were pulsed radars. It was deployed by the Naval Research Lab working with the Carnegie Institute. And, this predates Chain Home, and this predates goings on in the Second World War. And it's really maybe the first instance of perhaps of a pulsed radar, and it's being used to study the ionosphere. That was the use case. The Navy wasn't interested in a radar at that point. What good would a radar be for the Navy? But there was science to be done. And in these particular observations, though, the authors were probably a little bit dismayed because it didn't work very well. And if you notice these traces,
Dave,
yeah,
all I'm seeing is the picture of you.
picture of me.
Yeah.
I think the problem's on your end, Mary Lou. Maybe you need to
Oh.
adjust your windows.
Oh, okay.
Or at the top, there may be a view icon. And there you go.
Okay. So you see this now.
Yeah,
Yes.
looks
Okay,
good.
got
Great.
it. So first ionosphere observations of the ionosphere, these traces are giving you an indication of what the electron number density is as a function of height. But as I said, it didn't work too well because the traces are all spread out. And that's where this name spread F comes from. Not very creative name, but it was descriptive. And anyways, a bit of a mystery. The authors, Booker and Wells, wrote some prescient comments about what they thought it was. And they attributed the spreading to, small scale irregularities in the ionosphere and the ionospheric electron density, perhaps due to some kind of instability. Instabilities are mechanisms in nature that extract free energy and turn it into waves. And indeed, they were right. Henry Booker, by the way, after he did this, he went to Britain and got involved with their radar developments throughout the Second World War, played an important role there. And then he came back to Cornell, and he started a radio wave propagation laboratory here. And his students went on to build the Arecibo radio telescope and also the Hikamarka radar that I showed you in the past, a slide ago. So that's sort of the connection there. So now we have a much better idea about what causes this so-called spread F. So I'm showing you data from another radar. This is a radar in the Pacific, and it's a large, megawatt class sort of Thomson scatter radar. And it's actually showing a picture of electron number density in the equatorial ionosphere. And you can see that the F layer here has become corrugated, and what's happening is there's a kind of a convective instability at work, whereby low density regions from the bottom percolate to into the top side, and these irregularities wreak havoc for radio wave propagation. And this is terrestrial ground to ground propagation, satellite to ground propagation, GNSS. Space-based radio imaging, everything. And so this has become kind of the cause célèbre for space weather at low latitudes, and a very similar phenomena telegraphs into middle latitudes. So this is one of the things that I study. And if we look at the same phenomena with the Altair radar again, the top panels here are showing electron number density where the colors are kind of smoothly varying, and then where they're sharply varying, that's actually another scattering mechanism. That's Bragg scatter from very small scale plasma density irregularities, driven by plasma instabilities that fill up these depleted regions of the ionosphere. The curves beneath are measurements we made with a rocket. That's why we go to the Pacific. We launch sounding rockets to make in situ measurements, and these are measurements of number densities and electric fields. And without getting into the details, this is the kind of thing I study. This is the information that we need to develop and impose numerical models of these instabilities. And so that's something that I've been working on, fueled by radar observations, which we can make all the time, and rocket observations, which we can make every few years or maybe every decade or something like that. This is what the Hikamarka radar sees when spread F is overhead, and some of these panels, without going into too much detail, are showing electron number density, which is an important state variable, also vertical and horizontal plasma drifts, and the kinds of things that we need to pose a numerical model. For numerical models, you need initial conditions, which we get by sort of observing the background, and you also need drivers, and we get that with other kinds of observations. So without going into the details, all the important state parameters we measure with the radar, and then we try to construct models of what's going on. On the bottom right here, that's just sort of a time history of what the backscatter intensity looks like as this phenomena evolves. And so these depletions drift overhead. We get very intense backscatter from from the depleted regions of plasma, and I can make a little picture of that. It's not it's pretty, and it gives you the idea that you have plumes of low density plasma ascending up into the around the F peak and into the top side. We can do better than that by adopting some methods from radio astronomy. So what I'm showing here is actually imagery. So this is time is evolving here. You can't really see the time steps, but we get a frame every few seconds. And the colored patches, which will be a little bit more vivid in a minute, are showing us where the enhanced radar backscatter is coming from. And there they are. These are plumes of depleted plasma drifting overhead. So the cadence here is, once every few seconds. The resolution is every few kilometers. And so these are, with your mind's eye, you can say these are depleted regions of plasma that are full of small-scale plasma waves. And those plasma waves look very attractive when you look at imagery like this. If you're a radio signal passing through this, these irregularities cause diffraction and refraction and essentially cause our operational systems to fail. And fail they do, from GNSS to imagery to HF. And so that's the kind of thing that I'd like to work on, and the kind of thing that I'd like to forecast. So now I'm showing some numerical models. On the left is sort of an early state of the ionosphere, and on the right is a late state of the ionosphere. And you can see that the numerical model is able to capture this phenomenon of this convective instability, and not completely unlike convective instabilities that lead to precipitation here in the troposphere, but the physics is different. And so you can see sort of low density regions in the bottom of the F layer percolating up into the top of the F layer. And this is all well and good. And so we can develop numerical codes like this and get the physics right and sort of tune up the equations and run them on big computers and make predictions for what might happen. But one of the things that we need to do this is we need to know the initial state. So on the left, upper left panel there, kind of these kind of greenish and reddish colors, that's the initial configuration of the ionosphere before the instabilities have gotten working. And we really like to populate a volume in latitude and longitude and altitude with what the number densities actually are. And that's very hard to get from radar. Even a steering radar, a radar that can steer its beam around electrically or mechanically, it would take forever to fill that volume. It takes a while to make these measurements. The signals are very weak, even with high power systems, and it would take forever to scan around and fill up that volume in the sort of time that we need to initialize a forecast model. So what I want to really talk about today is another method that is not radar-based, but is radio-based, to make an estimation of what the electron number density is in a big sort of rectangular volume like that. And the way that we're going to do it is with HF, and we're going to do it with beacons. And so I'm showing you a map of Peru here where we deployed a bunch of HF transmitters and HF receivers. And so the key here is diamonds are transmitters. There are 3 of them, and circles are receivers. There are 6 of them. And they operated 2 frequencies. And these are very modest stations. I'll say a word about what they are in a minute, but basically antennas are dipoles. For reception, we could just use loops. The power levels are very low. And we use software-defined receivers. We use headers boxes to transmit and receive. And for the most part, it's the kit is very simple, and one person can deploy them and operate them. If you have power and network, you're good to go. And the idea is we want to consider all of the rays that are crisscrossing between all the transmitters and all the receivers, learn what we can from those rays, and see if we can use them to reconstruct what the ionosphere is overhead, in this case, over this sort of sector of South America. And so here are the details about the stations that we use. So in Peru, it's 6 receivers, 3 transmitters. The transmitter power is 10 watts. That's it. And I get these transmitters from Henry Radio. They've stopped making them, but you can buy 10-watt transmitters on eBay from Ukraine, it turns out, for about $100, and they're perfectly serviceable. We use frequencies that are kind of close to the 80-meter band in the States. Of course, I don't operate in the amateur bands, but the Peruvians assigned us a frequency right in the middle of the amateur band, so that's what we did. And so small stations, dipole antennas, we do a little trick where the dipole antenna can be made resonant at 2 different frequencies. And so we typically do 2 frequency experiments. And the main thing is that these things are coded. They're phase coded. And we use pseudorandom noise codes with 10 microsecond chips. And then the whole code repeats every 100 milliseconds. So it's a little bit like doing a radar experiment with a 100 millisecond interpulse period. It's just by being CW and never turning the transmitter off and using these long codes, we get a signal to noise ratio improvement of 10,000. So a compression ratio of 10,000. So it's as if we transmitted, 10 microsecond pulses every 100 millisecond with 10,000 times more power than we actually used. So that's the beauty of PRN coding. That's how GPS works too, and the reason that you're able to receive GPS signals from the distance that they are. You may know that a GPS transmitter on a satellite is running at about 50 watts. And the way that you're able to get decent signal noise ratios is by pulse compression, which is what we're doing here. And we want to modulate the waveforms because one of the observables that we want is time of flight. In fact, that's the most important one. And with a 10 microsecond chip rate, which is to say 100 kilohertz bandwidth, we get a range resolution of 1.5 kilometers. So that's our ability to determine basically the distance traveled by the ray, by the signal from the transmitter to the receiver. By the way, our experimental cadence is once per minute, and that long time delay allows us to get very, very accurate Doppler shifts. The high bandwidth allows us to get very accurate times of flight, which we convert to an equivalent range. And we also measure amplitude. In principle, we can measure bearing by using interferometry, and we can measure polarization if we use crossed antennas and collect both magnetic modes. In practice, we haven't done that, but we could. And here's what a typical data set looks like. So this is one transmitter, one receiver for a few hours starting around sunset. And what I'm plotting is delay. So that's time of flight times the speed of light and divided by 2 because we act like we're radar here. So that's like an equivalent monostatic range versus time. And we get a data point here once per minute. And what I'm showing you is the first hop off the F layer and the second hop and the third hop and the fourth hop as a function of time. The brightness of these pixels is signal to noise ratio. The signal noise ratio can be as big as about 30 dB. And the color is encoded in Doppler shift. So red things are red shifted and blue things are blue shifted. And it's just a few meters per second, but those are the kind of things that we measure. And so you see here kind of a well-behaved, smoothly varying ionosphere, except right in the middle. And right in the middle, that's when one of these depletions passed right overhead. And interestingly enough, for the most part, we were still able to track the first hop, and the system, retained lock, and we could still get our observables for the most part, even though the ionosphere was heavily disturbed. And that's because at these frequencies, sort of around the 80 meter band, for the most part, the rays go beneath the most disturbed part of the ionosphere. And so we can continue to get data even though the ionosphere is deeply, deeply disturbed. And if we'd been at a higher frequency, things would have been very dispersed, and we wouldn't have been able to continue to get this information. The channel basically would have closed. So we get, a set of data like this for every pairing. If we have N transmitters and M receivers and L frequencies, then the product N times M times L is the number of ray paths that we get. And for each one, the 3 observables, we get our time of flight, Doppler shift, and amplitude. And so that's lots of data. And we can run this for hours. And then what we want to do is this very difficult problem of deciding what the ionosphere must have looked like that produced this. But I think you compare this to WhisperNet or PSK Reporter. It's the same kind of idea. And in fact, the kit that we're using is really less sophisticated than amateur radio stations. The main thing is that we have a lot of bandwidth, more than you would get as an amateur. And these are GPS disciplined SDRs. And the SDRs have to be pretty good. We really can't tolerate any phase noise here. If your SDR has a phase lock loop in it, it's not going to work. And so these are sort of EDIS grade, National Instruments grade SDRs. So there's a certain amount of value involved in this, but it's not sort of outside the range of what a ham might have. So I want to talk about one event. This was back in 2022. I just happen to have data for that. And these are radar data. It's showing electron number density measured the way the radar does, which is, from Thomson scatter and, megawatt class radar to get this kind of information. And these aren't error bars. These vertical bars are just showing the scale height above and below the F peak of the electron number density. And there are a couple of periods here that are blacked out, and that's because the irregularities were so intense. The clutter from these ionospheric irregularities and the underlying instabilities caused the method to fail, basically. But this is one way of observing what we're trying to study here. The radar also measured vertical drifts and from Doppler, and this is showing on this particular night the ionosphere sort of ascended briefly and then descended, and then these sort of peaky areas are where these plumes drifted overhead and interfered with the radar method. We can look at GPS TEC. So these are a bunch of different PRNs, and what I do is I look at the 3 PRNs that are closest to zenith at any given time and plot their TEC. And there's information in here too about what the ionosphere is doing, and it's just these are path integrated values, path integrated between the satellite and the ground station. So it's a little bit ambiguous, but it is telling you that the ionosphere was kind of irregular at times, and there was some spatiotemporal variability. All of this is information, and what we want to do is take all this information and incorporate it into a grand, one model to rule them all that tells us what the ionospheric number density is everywhere. And here's what the HF observables look like. So this is just for one receiver, and I'm showing 6 different traces here, and the 6 different traces are 2 frequencies times 3 transmitters. So we have 3 transmitters running at 2 different frequencies. That's 6 signals that the receiver could receive at any given time. By the way, we're using different PRN codes with all of our transmitters, and that means they don't interfere with one another. They're all using the very same frequency band. They're right on top of one another. It's a 100 kilohertz wide signal. The Doppler shifts are only a few hertz, so these signals are right on top of one another, but they don't interfere because the codes are distinct. And so we can put as many different transmitters in the channel as we want, and no worries, it works fine. So the panel on the left is group delay. So again, it's time of flight times speed of light divided by 2. The panel in the middle is accumulated Doppler phase. That's Doppler shift integrated in time. And that's kind of a similar quantity to group delay, but it's distinct. It's telling us something different about the underlying structure of the ionosphere. And then on the right, I have received power on a sort of a relative dB scale. The signals actually fade quite a bit, and what I do is I remove the very fast fading. There's no way we're ever going to recover that with any kind of a model. And mainly what I want to see is sort of gradual fades that occur due to focusing and defocusing. As the ionosphere contorts, rays that are going into it and coming out of it can be focused to a point or defocused, and that affects their amplitude, and that's additional information that we can use to figure out the morphology of the ionosphere. So imagine, again, this is for one receiver, we have 6, so multiply all this by 6, and that's the information we get from the HF. Add to that the GPS data that we've got, add to that the radar data that we've got, which are telling us what's going on right overhead of the radar. And we have lots of information. So what do I want to do? So I've got lots of information, but it's all different. It's all heterogeneous, it's all kinds of weird stuff. And what I'm going to do is I'm going to build a model of what the electron number density is in the ionosphere in this big, rectangular volume. And there are any number of ways to do this, but I'm just going to say it's parameterized, and it's expedient for me to parameterize the electron number density with 1125 parameters. So by setting those numbers appropriately, I specify what the ionosphere looks like with some spatial resolution. And why it's 1125 is not particularly interesting, and there are any number of ways I could do that. But let's just say with 1125 numbers, I could parameterize what the ionosphere looks like over Peru, in a volume over Peru, and with some spatial resolution, which is a few kilometers per voxel, basically. Now that's a lot more parameters than I have data, actually. The number of data that I have, the number of observables of the order of 100, if you take all the HF data and the GPS data. So it's an underdetermined problem, but that's okay. There are methods for dealing with that. And what we do is we find basically, there's an optimization problem, and we find the ionosphere that agrees with the data that we've got and is simplest. And there are different metrics for simplest, but basically the curvature of all the parameters is minimized. So it's sort of the least remarkable ionosphere that you can specify mathematically that's consistent with whatever data you got. And the data come from HF, come from ionosons, come from the increment scatter radar, the large high power radar, and from GPS TEC. And the way that we do that, and I don't want to get too mathy here, the way that we do that is geometric optics. Geometric optics has been around for since the 1830s, I guess. And essentially what we do is we treat the signals that are propagating through space ballistically. And we write down, we draw rays corresponding to a path that goes from the transmitter through the intermediate volume to the receiver. And those rays follow a ballistic trajectory as if they were, rocks falling through gravity, through a gravitational potential. And here the potential is different. It's based on the index of refraction of the ionosphere. And we can write down these ordinary differential equations. K is the wave vector for the ray, and you can think about like that as the momentum of something that's falling ballistically, and X is the position of the ray, and that's like the position of something that's falling ballistically. And then the potential field that they're falling through depends on this thing H, which is formally called a Hamiltonian. In this case, it's something that describes the medium and the index of refraction in the medium that we're propagating through. And that index of refraction depends on lots of things. It depends on K and X, it depends on frequency omega and time t, depends on the electron number density, the magnetic field, which we know, and the electron neutral collision frequency, which we say we know. And so these are equations that you can use to take a ray from initial conditions, from initial coordinates where there's a transmitter, propagate it through the ionosphere, propagate it all the way down to terminal coordinates where there's a receiver. And when you're done carrying out that integration, you will have a prediction for all the observables. You can predict all the observables. And I'm not writing down those equations, but those are other equations we have to integrate. But you can predict what the group delay would have been, and what the Doppler shift would have been, and what the amplitude would have been if the ionosphere were a certain way. And so this is just a little sort of toy model of what that looks like. So you start off array at some initial location where you actually have to have a transmitter, propagated it through a candidate ionosphere that's specified by my 1125 points, let it do its thing, come back down, fall to the ground, and oops, it didn't hit the place where the receiver was. So you do it again, and you do it iteratively, and you keep doing it until the ray path does hit the place where the receiver was. And at that point, you'll have a prediction for what the receiver would have received if the ionosphere you propagated it through was the right one. And now there's a bit of a problem here because you have to sort of tune the initial trajectory of your ballistic path here so that the ray falls where you need it to fall. And that means you have to calculate sensitivities. That means you have to say, how would this have been different if I had launched it at a different angle? And it turns out you can write down equations for these sensitivities and integrate them too. It's just very, very, very complicated. And the math is horrendous. And during COVID, I had nothing to do in my dining room. So I actually powered my way through these equations, and I filled up a notebook. And some of them were wrong. And, only through trial and error and consistency checks and so forth did I fix all my errors, because there was pages and pages and pages of formulas. And that's how I did my sensitivity analysis. I came up with the equations that tell you how to change your, the initial bearing of these rays so that they fall where you need them to fall, where you have receivers. And it turns out I didn't need to do that. And so I want to just mention one thing that I used here. I'm just going through mathematics. I'm not going to talk about it. It's just very complicated. Don't pay attention to any of this except the last line. It turns out I discovered something during COVID, and that is there's a tool out there that everybody should use who does this kind of work. And it's called automatic differentiation. And what automatic differentiation does, automatic differentiation is what makes machine learning work. It's not machine learning, it's what makes machine learning work. And what it is it's a computational way of figuring out, for any computation that you're doing, how the output would have been different if the input had been different. And at the bottom, what I'm showing here is actually a line of code, and this is in C, but it doesn't matter. And what I'm doing is I'm calling my function. My function is called function ray, and that's the function that's going to trace rays from the beginning to the end, from the launching point to the terminal point. And that function works. And for a candidate ionosphere, that function works. But I pass this call, called automatic differentiation to a library. And what that call does is it takes my code and it interprets it. And it says, I know what you're trying to do there, Hysell. I see everything that you're up to because I've got your code. And I see what you're trying to calculate. And I'm going to go through, I know the derivatives of of elementary functions, and I know the chain rule, I'm going to calculate for you how the thing that you're asking me for would have been different if you had given me different inputs. And then it spills out the answer and it gives it to you. And it gives it to you, the answer to machine precision, and you don't have to do the work. And so suddenly, by using automatic differentiation, the length of my code was shortened by about 3,000 lines. And I got the same answer. And so I just want to point out to those of you that are interested, automatic differentiation is the tool that makes machine learning work, but we can use it for anything. And that's it shortened my analysis code vastly. And so now I'm going to show the results. So again, the idea is we have all these rays, and we trace them from transmitter to receiver. If we have a candidate ionosphere that is based on 1,125 parameters, the code predicts what I should have seen in my receivers, the time of flight, the Doppler shift, and the amplitude, if my ionosphere was the right one. Of course, it wasn't the right one. So it goes back and it changes it. And it changes those 1,125 parameters until all of my observables match, all my predictions match. And at the end, I get a picture of what the electron number density is in the volume. And this is what it looks like. So these are isodensity curves. And each one of these surfaces is, a few times 10 to the 11th per cubic centimeter electrons. And this is showing the ionosphere is tilted a little bit from west to east. It's not tilted from north to south. And this is what I get for 1 minute of data. But we have lots of minutes of data, so this is a movie. And I'm going to start it off here. And there it goes. And this is the evolution of the ionosphere. And so the ionosphere is rising, just like the radar data said that it was. It's pretty laminar. It's pretty flat. It's just sitting here rising, minding its own business. After a while, it's going to start to descend. Remember, I know the electron number density everywhere in this volume, and the easiest way to plot it is with isosurfaces like this. Eventually, it's going to start to descend, and then a big sort of pulse is going to move through it, and it's going to move from west to east. So we have to wait for that. The ionosphere is descending now, descending, as it does at night. And then this pulse moves through. So it's uplifted to the west, and then that uplifted region, passes through to the middle. It'll do that in a minute. And then it passes out to the right. And what we're seeing is one of these depletions moving overhead. And the radio waves are passing beneath it. So we're really recovering the electron number density mostly beneath it. But lo and behold, it's captured the same kind of information that we're getting from our other observables, but it's capturing over this huge volume in the way that the radar couldn't. The radar's seeing what's basically directly overhead. And, with pretty good cadence, once per minute, and with pretty good spatial resolution, a few kilometers or tens of kilometers in every direction. And that's all with HF, all with HF. The total cost of equipment deployed here was, $50,000 or something, as opposed to a $50 million radar. And, pretty nice. And all using kind of technology that hams are familiar with and would be comfortable with, and could even be afforded. Recently, I deployed some transceivers in Alaska. There's different space weather in Alaska. It's a little bit harder environment, really hard to service equipment in the winter. But we have 3 transmitters and 3 receivers. And so it's a smaller network. Alaska is a harder place to do this kind of research because there's always, particle precipitation in Alaska. And that drives the D region up, and that drives absorption up. And so there's just kind of a brief interval every day around twilight when there's enough ionization around for us to see it, but not so much absorption that we see no radio signals. And nonetheless, we're able to do the same kind of methodology here. I won't walk you through everything, but this is what we got. This is all sort of post midnight. And so I'm showing a bunch of isodensity surfaces here. These are separated by 20 minutes. So we're looking at about an hour and a half worth of data. And what we're looking at is the main ionospheric trough. So at high latitude, sort of between the auroral zone and the subauroral zone, there's a bite out in electron number density for sort of well-known reasons. And in this first frame up here to the upper left, you see there's more density to the north and to the south. And so we're sort of looking at the northern edge of the of the trough. And as time goes by, it sort of shifts around a little bit. And so that by later in the event, we're kind of looking at the southern edge of the trough. But the main ionospheric trough is a sort of a major feature of space weather at high latitudes. During geometrically active periods, irregularities at the walls of the trough, or where scintillations occur, where radio degradation effects are the strongest, and so forth. And again, this is sort of a huge region of space that is, it would be difficult to probe otherwise, but with a few HF stations, it's possible to do it. And I'm showing these things at 20-minute intervals, but the cadence is once per minute. So I could show you a movie of this too. And now there is a high power radar in the field of view of our HF stations, and we did use those data. It was very intermittent. It was sort of on and off all night long, and so we didn't feed those data into this analysis, but what I did later is I validated. And lo and behold, we matched the radar. So $50 million radar, $50,000 worth of HF stuff, and I think we did pretty good, and managed to specify the electron number density over this large volume of space. Perfectly suitable to drive numerical simulations, to initialize numerical simulations of space weather, which is the goal. So I have some summary conclusions here. The network is fast, inexpensive, practical ionospheric specification for space weather modeling and forecasting. The electron density is inferred from HF observables by solving an optimization problem that involves ray tracing. Sensitivity analysis is normally computationally expensive, but with automatic differentiation, what was a very, very, very complicated code that I couldn't read anymore became rather simple. So all the code that I'm using to analyze these data is of the order of 1,000 lines long. It's really not much, and a lot of that is just data I/O. It is parallelized, so we run on a big cluster, but that's not a big problem anymore. And the main thing is that more HF is better. And 6 stations is okay, 9 is better than that. I'd really like to have 100. And that's, I think, where ham radio comes in. And it is really logistically difficult to keep equipment in the field, particularly in Alaska. Power fails all the time. Network fails all the time. Antelope knock antennas over all the time, and keeping, if you have 6 stations in the field or 9 stations in the field, the chances that they're all working on any given day are very low. And I'm also getting older, and endless field trips to keep kit like this working is less and less attractive every year. And what I'd really like to do is to outsource this, and I'd really like to outsource it to some enthusiasts. And I can imagine a situation where maybe my group or my colleagues, we field a few transmitters in the continental United States, but we let other people do the receiving for us. And so you don't need a license. And these are all licensed. Our stations are licensed under the FCC experimental program, which is very generous. It basically, you tell them what you want to do, give them $100, and they say, great. If you interfere with anybody, you have to stop. And we don't interfere with anybody because we're using disused bands. You may know the shortwave bands are empty. And so it would be pretty easy to set up in the continental US, say, 3 or 4 or 5 transmitters, and then let the community do the receiving. And I could imagine a situation where, we have a kit, and you apply and you get a kit, and it arrives in the mail, and it's a tiny computer and an SDI, a software-defined receiver, and a loop antenna or 2 and some coax, and that's it. And you provide the power, and you provide the networking. And then, we run this thing all the time and just download data from people. When the data are available, that's great. When they're not, they're not. And then we build ionospheric models in something like near real time, say over the continental US. So it's a little bit like WSPR or PSK reporting, and but it's a little bit different. It's more, what's really important here is that the quality of the data it's got to be really good. It's got to be uniform. And it's got to be really low phase noise, like I said. It's got to be GPS disciplined, but I think it's doable. And so I'd like to sort of entertain a situation where we do something like that. Now, maybe it's possible to do this purely with amateur transmitters, receivers in amateur bands. I have to think about how to overcome the bandwidth problem. It is possible to get the kind of resolution that we need with less bandwidth by averaging, by integrating for a long time, but then you lose cadence. So we'd really like to have all of our observables once a minute, and it's going to be hard to do that with the kind of bandwidth that amateurs are allowed to use. But maybe there's some possibilities there, and otherwise, maybe I could have a situation where again, you know, receive stations are made available to people who are interested, and they agree to deploy them, set up in the backyard, give it power, give it network, and maybe could put out 100 stations, and even if every station costs a couple $1,000, that's not undoable. That's doable, I think. So that's kind of my proposition, and I'm going to stop sharing and be happy to take any questions that you have. And really, I'd like to discuss either premise, either using um, amateur equipment, let amateurs use their own equipment to try to do something like this using existing modalities, or use equipment that our group would supply or some agency would supply in order to get these kind of specifications. So I think I'll stop there. I'd be happy to take any questions you have.
Thank you so much, Dave. That was really wonderful. So, can you hear me?
Yeah, I can. Good to see you, Nathan.
Yeah, you too. Yeah, great to see you also. I think the receivers we're deploying now as part of the Personal Space Weather Station project should be capable of doing the receiving you want already. And if not, I think they should be able to, with a few small modifications, they might be capable, because we're GPS disciplining them. We're working on putting in a pulse per second timestamp signal into it too, which we don't have yet, but I think we're close on that. And we have the network infrastructure to collect all of the data and to save it in digital RF format. That's all time stamped and everything, and we can basically specify what bandwidth you want to record and what frequency you want to record. So wow. I would think that the project that we already have to do these deployments, you could tell us what frequencies you want us to listen to, and we could hand you the data.
Wow. Well, that's terrific. So where are you deploying, and how many stations?
All over the country. So there's already a number of stations already deployed, and I'll let Rob Robinette, who's on this call, he's the one that's led really a huge volunteer effort. And then we're in the process of deploying another 25 NSF funded stations right now. Wow. So maybe Rob, do you want to speak a little bit about what stations are already deployed?
Yeah, on the receive side, I've developed a system with a tremendous amount of help with others that consists of a RX 888 16 bits A to D, clocked at 126 megabits. That is driven by a Bogner GPS DO. And each receive site can record literally dozens or hundreds of different channels simultaneously. So we could record your existing signals, easily add them as additional channels to be received, processed, and uploaded. We have plenty at each receive site. There are 63 active receive sites now distributed around the world. We have sites down in Antarctica at the German research station, up in Ellesmere Island in northern Canada, that's operated by the Canadians, and then receive sites in the middle of the Pacific. Just everywhere, Europe,
and what do you normally receive? What stations are normally?
Well, our initial targets was whisper receptions, so they're now they receive all of the whisper bands simultaneously, continuously at all times, and decode them and upload them. Both the whisper modes and the other modes, the FST4W modes. The 4W offers increased frequency resolution. We get a tenth of a hertz resolution of the received signals out of 4W receptions. Although there's relatively few transmitters, transmitters, we do have a companion transmitter that is a eight output simultaneous 1 watts GPS disciplined to whisper sound 8. And this is a GPS disciplined simultaneous 8 channels. And we for example, operate one of those at WWV. there's a such a transmitter, and it's in the building with the WWVB building, and we have a multi-band end-fed antenna, and it's actually the most reported whisper beacon in the world by far.
I see.
In part because it transmits continuously. Every whisper 2-minute whisper cycle on all 8 bands are being transmitted. So as a result, all receive sites, about 40% of the whisper reception reports that are uploaded to whispernet.org come from
Yours.
from our receive sites,
I see.
and
Amazing.
and virtually all of the 63 active receive sites using the RX888 are GPS disciplined and
Mhm.
upload lists. So they're listing on all the bands, and those receive sites are. Nathaniel has shown you a map that shows some of them around the United States, but we have others around Europe, Tasmania, South America, Antarctic, and the Arctic, and we're adding to that network all the time. So those receive sites consist of this RX888 16-bit A to D sampling, and the data is very much validated. We go through and ensure that everything we upload. So that's the whisper part of it. In
Mhm.
parallel, these sites are also listening to all 10 of the time signals, the WWVB, all the WWV from Fort Collins, Hawaii, and CHU are all being received and recorded. Those are recorded. IQs are uploaded, and you can see the resulting. Of course, they're decimated to 10 hertz at the end of
Mhm.
the day, and uploaded to this PSWS server site. But the raw data, the 16 kilosamples, I think we're moving to 20 kilosamples for the WWV channels. All of that raw data is cached on the individual sites. So we could go back, and if there were an interesting event, you could go back and ask for the raw 16 kilosample data for
I see.
within a reasonable period. Some sites are go back 6 months, but most people have a few days, the last few days. It's just the data storage issue. How much?
Well, this is tremendous. So I should work with you and Nathaniel and see if there's a
Mhm.
way to sort of make this work. Of course,
Uh,
I don't have any transmitters in CONUS right now, and Alaska would be a long haul.
yeah.
Yeah.
Well, yeah. Well, we hopefully, we do have we have one of our sites is in northwestern Washington, so your
Mhm.
signals might be available there. I don't know if
Mhm.
it's a single SIP
And
distance here. Mostly, you're interested in the single hop reception, right? I mean, it's
Yeah, that's in principle we can do multiple hop, but the computations just get astonishingly more complicated. And so, really,
yeah.
what I'd like to do is stick some transmitters in CONUS and have an area sort of surrounded
Well,
by
well,
receivers. But that'd be perfect.
well, well, I don't know that our the creator of our transmitter, the Whisper Sound 8 transmitter, is created by one of our colleagues, collaborators, Paul, WB6CXC, and it's entirely a digital device. So if we want it, it could be repurposed to transmit other signals.
Oh, I see.
We could conceivably either in fact, our group has been discussing how to introduce time of flight modulation
Mm.
data, modulation into the existing, whisper. There's certainly the 10-second gap, at the end of the
Mhm.
whisper cycle where
Mhm.
we could put in a PN code signal there without disrupting anything else we're doing, or we could just drop sending not send whisper signals and send PN codes on, and we are to that extent, unless we had operated under your part 5,
Mhm.
we could do that. I mean, it's not frequency sensitive. These are the output of these. There's 8 individual transmitters. They go into a combiner. There's a Paul designed a combiner. I don't know if you'll see it there, but yeah, 9-band combiner. We take those individual outputs and then bandpass them, and the output of that goes to a single antenna. Now, that is optimized for the ham bands, but I know Paul would be happy to rework his design
Mhm.
to match the requirements of your application.
So typically we work pretty close to the ham bands just so I can use amateur radio antennas.
Yeah.
So they might work just off the shelf.
Well, then it's very possible that we could. I think we have in stock in Scranton. I think there's something like 10 of these transmitters sitting there, looking for deployment locations.
Yeah.
So if there's a, I mean, the limitation of his ability to modulate this, I guess Paul isn't part of this. I think it's unfortunate he isn't here, but Paul's been looking at how wide a bandwidth signal, how quickly can he basically has to reprogram.
Paul will be at AGU, so if you want to talk to him in person,
I think we should get together at AGU.
I'll be at AGU too. I can look out for you,
Yeah, Rob will be at AGU also. So we're all in a session on Monday morning at 8:30 a.m. bright and early.
I won't be there.
But we're going.
I can look for you at the break.
That sounds great. We're going to dinner Sunday night, so let us know if you want to come to Sunday night dinner.
Yeah, no, unfortunately I'm flying in Monday afternoon, but I will look for you guys, and we should make some kind of a plan going forward. So bandwidth is your friend, and like I said, we are outside the bandwidth that is normally afforded to amateurs in HF, but you can cheat a little bit, of course, by stringing together multiple transmissions.
Well, there's nothing bandwidth specific to the transmitters or the receivers.
Yeah.
On the receive side, we can continue to do what we're doing now with WWB and add a reception of your signals as well. That whisper response obviously can't transmit both. So they can only transmit 8 different signals simultaneously. Yeah. So on the transmit side, we do have a constraint, but on the receive side, we have no constraints. And I assume that a Bogner provides enough frequency, accuracy, and phase noise. Accuracy that it would match your requirements, but all of this is adjustable.
So I have a real dilemma in that we've been using Edis equipment really for 20 years, and now the N200s, N210s, and all of that line is gone, and so I'm really very sad. I snatched up as many as I could, and some of my colleagues did the same. So they're all pretty much gone, and so I'm trying to figure out new platforms to replicate all of this. And one thing I did discover is that there's this outfit called HamSCIence that sells basically a GPS DO that's almost identical to the ones that was in the USRPs, and they sell for $100. So I've gotten a few, and I'm going to experiment and see if they actually work. And the company that sold the GPS DOs to Edis will sell you one now. Will sell one direct to you, but they're not cheap and they want high volume.
But it'd be. Are you familiar with the Bogner and its performance?
I'm not, no.
Okay, well that's what we've been using, and but we'd love to have something lower cost than that.
Yeah,
and that costs us $200 each.
Yeah, that's not too bad.
Yeah, it's not too bad, but it's the Bogner is a high quality device, but it isn't. It's not a temperature controlled GPS, frequency oscillator. Inside it has just a temperature compensated.
The one that I got from HamSCIence, which is a funny little outfit, is actually it's oven controlled. So and that's something that
Actually, the oscillator that's built in the ARX 888 receiver and that we use, the SDR, that receiver is that you show it really has only an A to D and a USB 3 interface chip. That's it.
I see. Yeah,
that's all. Good.
That's advantageous. That's good.
Yes, yeah, and in fact, Paul is working on our own version because the 888 has thermal problems, and we don't know who makes it, and there's the provenance is poor. So we are working on I think several of us are working on several designs. Now, I don't know to what extent your application requires orthogonal reception, because this is a single channel device.
Yeah, I see.
Okay, now we believe it's possible to driving the same clock to both of them, and Paul has, and we are testing a time signal injector sidecar, and with that we can get sample accurate timing, and that could be fed to both, two of these 888 receivers, and software could then align the samples. It would be aligned in software, so we could obtain that's one path to orthogonal reception. But one of the HamSCI members, Tom McDermott, is it? I think is been developing a receiver using a 4-channel A to D, and that would be much cleaner approach to orthogonal reception. So we are zeroing in on temporal accuracy, and then we have a path to multiple antenna systems.
Well, why don't we get together and chat and see what might be done? I'm just curious if does anybody have any questions while I'm still around? I feel like we've been having a private discussion here. Does anybody have any questions about anything that I could address that might be interesting apart from that?
I have some questions. Yep. Okay. Always happy to listen to your talk. A lot to learn. Yeah. I have a couple of questions, and some of them relate to how, when you use the HF, say in the lower frequencies, say between 2 and 5 megahertz, they go up to really the bottom side, F1. But spread F, I think, has the perturbations or the waves which trigger in the F2, and that's when the irregularities start. I might be incorrect. So when you are supplying the background ionosphere, which is developed through, say, HF, does it give only E and F1 layer, and how can we interpolate the F2?
It does. Well, actually, it can get into the F2 layer. It really depends on how developed the ionosphere is and what time it is. But the model has to have some other information. So it gets the F peak and the topside from the sounders, GPS TEC, and the radar. And just the fact that the radar is profiling the entire ionosphere, GPS TEC is going through the entire ionosphere, and the sounders making it up into the F peak, all of that goes into the model.
That's
So we have to have some information. We actually do get the topside and around the F peak, but it's not coming from the HF. But the HF, in a way, is really important to us because it's that's kind of the key area for figuring out how signals are going to propagate, and ultimately interested in degradation of signal propagation. But you're right, that's a very good question.
That's true. Awesome. Now, lots of questions, so maybe I will meet you at AGU. And
okay, maybe I'll see you at AGU.
Yeah. Now, the second thing thought which I had was, you had the ionosphere which was built up, and you had the iso electron density contour or labels. And then there was an uplift around 19 LT. That could be because of the PRE or pre-recent.
It was the PRE, yeah.
But what you had at 21 UT, what was at 21 LT? Was it a prompt penetration which uplifted everything, or
it was the base of a plume, and the rays were able to make it back to the ground, but it was the base of the plume, and we saw the plume in the radar. So what's interesting to me is that it didn't destroy the HF signals, the HF observables. And that's because our frequency was low enough that we were able to get, for the most part, propagate beneath it. But it was an uplift associated with the plume.
Oh wow, nice. And one more thing. In those 1125 parameters which you use, does it combine all the, say, radar, GPS, and HF, or is it okay? And in that, when we say try to adjust the transmit receive locations for the radio propagation, do you assume that it is only the one hop goes up to the ionosphere and comes back, or do you assume the second hop also?
So we can see multiple hops, and in principle, we could use multiple hops. And I have a student that worked on that, and he's doing kind of similar work. His work is different. He wants to use this idea, go one step further, and actually use this as a replacement for GNSS. In other words, you turn on your HF, you acquire your data, you know what the ionosphere is because we encode these 1125 coefficients in the signal. And then you can figure out where you are as if you're using GPS. And the idea is it's GPS without GPS. It's GPS just by listening to HF. And in order to do that, he wanted more information. So he uses multiple hops. Multiple hops really makes your life miserable because you have to consider all the places that the hops might have been. So I don't do that. And really, I should find the courage and do it. It's going to grow the code tremendously. But you can see where the multiple hops are in the range sorted plots that I showed you. And often we get 2, 3, 4 hops.
Okay. Thanks a lot. And I will look forward to meeting you at AGU.
Yep, great. Thanks very much.
I have a question. Thank you for a most inspiring talk. I'm a pure amateur in this group with a background in oceanography.
Mhm.
And some of the observations I'd made could see compressions and rarefactions in the Doppler shift inferred heights at two frequencies. But then I was somewhat taken to task very kindly that compressions and rarefactions shouldn't be allowed by magnetoionics theory. Do you
Yeah.
have any comment on that?
No, the flow is incompressible. That's right. The flow is very nearly incompressible, and uh, I think you cannot make conclusions about compression in the fluid on the basis of these lines moving closer and farther. Essentially, you can have compressibility in a plane, but not in the volume. And I think you may be inferring compression in a plane, but that's not compression in a volume. But you're absolutely right. The flow is incompressible.
Even though your images were showing wonderful compression and rarefaction.
But you don't know, basically the fluid is squirting out the edges.
Ah,
Yes, so and that's allowed, and that in fact does happen. So the bottom side can get steeper. It's a very good question. The bottom side can get steeper and shallower, but it's
yes.
squeezing out the edges, and it is incompressible.
And
Yes,
how
great
might you
question.
visualize that?
Pardon me?
How might you visualize that?
Oh, I'm a really horrible visualization. What I really need is somehow a way of communicating three-dimensional number density in a way that's sort of semi-transparent. I guess I could put in little flags showing flow.
Right?
So we simulate this numerically, and what you're saying is exactly right. The contours approach one another and depart from one another, but there's flow squeezing out the edges, if you like.
Right.
Yeah,
Okay. Thank you so much. Thank you.
you bet. Mhm.
Excellent. Any more questions? We're nearing the top of the hour. Yep, Glenn?
Thanks, Dave. That was tremendous. I really appreciated the
Your
animation.
audio is very low, Glenn.
All right, hold on. Hold on. There we go. I'm back.
There you go.
Okay, Dave, I appreciate it. Great animation. Right, it really, and then your description about how it squeezes out the edges. When I'm on the bands, the guys ask me, "What is the ionosphere doing today? What's it doing?" And I give it to them in usually two or three different ways. One, it's egg drop soup, right? It's got a very soupy consistency, but you're going to hit blockages along the way. It's oatmeal, turn the radio off.
Mm.
It's tomato soup. It may have some paths through it. So they ask me, how soupy is it today? Right? I tell them, well, it's a nice clear broth. It's
Mm.
the only way I can get these guys to understand the simple hand, right? To get them to understand what's happening in the ionosphere. They look at 700 different parameters and they can't figure out what to do. What band do I
Mhm.
go on? What's good today? Where's the second hop? A lot of times I'll be on the air and somebody will ask me, how far is this? I said, first hop is 600 miles, second hop, 13, third
Mhm.
hop, 2,700 miles. You could talk to Hawaii right now,
Mhm.
right?
Mhm.
And that concept of that, it has to be made simple for the average ham. If we're doing anything, we've got to be able to explain this, right? Just
Yeah,
so
very good.
people can get the value out of what this is. But
Yeah, I would say not just the average ham. There was a time not so long ago when, you know, the armed services were experts in radio wave propagation. Then satellites came, and now nobody knows anything about radio wave propagation, and it's a real challenge because um, there's a widespread belief that GPS will be the first thing not to work when there's a crisis, and so there's a lot of interest right now in regaining expertise in HF communications. And I have friends that have been staring at manuals for modems, HF modems, and trying to figure out what on earth the channel capacity of an HF system is. And this is the sort of thing that people used to know a lot about, and now scarcely anybody can recognize the equipment or the concepts. So I think what's old is new again, and there's renewed interest in sort of trying to figure out how to make these things operational and how to communicate that simply.
thanks, thank you.
So great, thanks.
Wonderful.
Quick one.
Yes, John.
Thank you very much, John W3MHZ. Thank you very much for a fascinating talk. I was watching with a lot of hams, your colleagues, on their light sail mission this week in the CubeSat and following along on VHF. I have a very simple question. I'm very humbled by the knowledge here, but I look at the frequencies 2 megahertz, 4 megahertz, 5 megahertz. That's pretty much a long antenna, right? That's what's best for this operation. It's like a long dipole antenna for 80 meters, 160 meters. Is that it?
So for transmit, yes. For receive, we use loops, and loops are very inefficient, but they're small. And the reason we can get away with that is the sky noise is tremendously strong, and that means that you use an inefficient loop. That's fine. You throw out most of your signal, but you throw out most of your noise. The SNR is preserved, and the noise is still much larger than the noise in the receiver, so there's no penalty. So on reception, we have very modest loop antennas.
How big are these loops?
A meter.
Oh,
Tiny.
wonderful. Great.
Yeah,
I'm interested.
the impact is very small. Yeah, there you go. The impact is very small, and it works fine. And as I said, you can't do that for transmit. So we have basically we have big inverted V's for transmit and loops for reception, and that's just fine.
Great.
Little
I'd
loop.
love to poke your pen. Thank you.
Yeah, great. Thank you. Great call, John.
All right. Well, at the top of the hour, I think we'll let David go and everyone go. Thank you very much again for a very informative talk. And I think the recording will get a lot of views, both in the near term and in the long term. So that's much appreciated. Also, all the attendees, thanks to those of you who are here with us pretty much week after week. And if this is your first time attending, we hope you enjoyed it and you will join us again. Our next formal speaker will be on January 8th. We'll be talking about WSPR and WSPR equipment and its capabilities. So we know exactly how low can we go so far as pulling some of those signals out through WSPR. Unless there's any last comments, we'll call it a wrap and say everyone have a great holiday. I'm not sure if we'll even have a call next week or we'll get together again on the 8th, but the HamSCI group will announce our intentions there. All right. Thanks, everyone.
Thanks,
Great.
everyone.
73.
73.